All right, so as we wait for maybe a couple more people to trickle in, I'd like to ask a quick question. How many of you, this is your first time here at CppCon? That is a lot of people, that's great. It's my first time here too, and actually as I was flying in on Saturday, I was greeted with a nice rainstorm. It was great. I say that because in upstate New York, where I'm from, we're actually in a severe drought, and we haven't had real rain in a hell of a long time. So really, if I'm going to bring something back from CppCon to my colleagues, I'm really hoping I can bring some rain. That would be kind of great. But we're not going to talk about rain today, besides that. Instead, we're going to be talking about iteration. And you know, it's a 9 a.m. session, and I figured the best way to start a 9 a.m. session is to have an audience participation section. So I'm going to ask you guys to just raise your hands if you agree with the statements you see before you. All right? And I'm going to start off with, I've heard of iterators before. Raise your hand if you've heard of iterators. Great, okay, you're in the right place. And in fact, how many of you have used iterators in your projects before? That's a good number, great. How many of you like iterators? Okay, fewer, some, I saw some on the fence. How many of you love iterators? That's a lot fewer. How many of you really, really love iterators? Just Marshall, right? And in fact, how many of you think that iterators are fundamental to computer science? Yeah, I see a couple hands. Well, I actually think all of those things. And I'm going to try to convince you of not all of them, unfortunately, but at least a couple of them. So when we leave this session, you're going to have heard of iterators before, or have by now. You're going to have used iterators before and see how you can use them to write generic software and software that will work across any number of data structures and algorithms. And hopefully, but maybe not, I'm going to teach you to love iterators. I really hope so. Although I won't be really talking about how iterators are fundamental to computer science, if you're interested in that, come talk to me offline, and I love to talk about this sort of stuff, all right? Okay, so how are we going to get there? Well, this talk has two main sections, all right? The first part is Iterators 101, and we're going to be building up iterators from zero. And we're going to be looking at algorithms and seeing how iterators fall out of those algorithms and how we can get very generic software just by looking at these algorithms. It's going to be great. I really love this. And this is based on a class that I teach. But the second part here is actually kind of cool too, and I think some of you might be here for that. We're going to be talking about how we can take the iterator hierarchy as it is today and extend it to allow us to write cache-aware, parallelizable, generic software. All right, and how are we going to be doing that? Well, we're going to be doing that with a paradigm called generic programming. Now, if you've used iterators before, you might have heard of generic programming. Generic programming is, well, we'll see examples of it. And the way we'll be doing that is using the new concepts light technical specification syntax. And we'll be talking about concepts light, we'll be talking about concepts as they relate to concepts light, and what we can do to write very generic software using this TS. But I want to make clear that this is not an introduction to the STL. In fact, the iterators I present are not the STL iterators. They're very similar. But if you come out of this talk and write this in your code and just pound include stood algorithm, it's not going to work. All right? But you're going to have the tools that you will use to understand how the standard algorithm works, how the ranges TS is going to work, and how any iterator library will work. And furthermore, we have an hour. We're not going to do a comprehensive guide to concepts light. You're not going to learn all the ins and outs of the syntax and the semantics of it. That just would not be feasible. All right, so, and finally, we have a lot to get through. One of the nice things about being in a big room like this is we have microphones up at the front. So I'm actually going to defer all questions until the end, if I can. And at the end, if we have time, please come up to the microphone and ask questions. If not, come and find me, and I'd love to answer your questions. All right, so let's start out with Iterators 101, right? So we're all C++ programmers here. If I show you this algorithm next, you're not going to be surprised at all. This is a really simple algorithm. It takes in 4 pointers, 2 of which form a range and 2 of which form another range. It loops through those two ranges, and just assigns from the input range to the output range. Is anyone surprised? Great, okay, so this is good. So this is a really easy to understand algorithm. Why am I even making this a function? I mean, this is just a while loop, isn't it? If you were writing this yourself, you'd probably just write a while loop. You wouldn't say, oh, I'm gonna break this out into a different function, call it copy. Because the while loop's pretty clear. Now, we do actually get a nice benefit of breaking it out into copy, and maybe it's worth it. We actually say copy in our source code. When we're looking at the call site, we don't have to parse through a while loop. Now, the while loop is pretty easy, but we don't have to parse through a while loop and see what's going on. That's pretty nice. But can we do better? All right, well, unfortunately, I know the high-performance computing guys would really love this, but we don't just work with arrays. In fact, I've had to work with data structures that look like this. I think a lot of you have. This is a singly linked list, right? It's not an array, unfortunately. But we can still write a copy algorithm that takes some segment of a linked list and some segment of another linked list and copy the values around. In fact, we can even take some segment of a linked list and copy it into some segment of an array. This is really easy. And again, you would just write these while loops, right? Why are we breaking this off into a function? Well, we'll see. Now, some more interesting data structures that we work with, at least some of us work with, we go out over the network and we write something out over the network, or maybe to disk, or maybe we stream something to a console. Again, this is just a while loop, isn't it? Instead of taking pointers, we're taking an ostream ref, but as we write this, it looks very, very similar. Now, anyone in this room could write any of these algorithms. So why am I showing you this? The 4 algorithms we saw were really simple to write. In fact, any of the 9 of those permutations are also really simple to write, right? And 9 functions isn't that bad, right? And we unit test them, right? We unit test them. Yeah, we unit test them. So we know that they work, and that's pretty good. I hear some laughs. Okay, this is great. Unfortunately, though, I have a confession to make. These are not the 3 data structures that I've used. In fact, sometimes I use a W linked list too. And sometimes I even use an in-order traversal of some sort of tree. Or maybe a standard deck. Or any other sort of data structure you could imagine. Maybe we have a function that just spews out data, a coroutine that just spews out data, and we want to write that to an array. 50 functions, we can still do that, right? We can still unit test those. We can still make sure they work. We're great, right? That's not that long. Until, we want to, we're porting to C++11 and suddenly we add move semantics. We want to move from our input range. Or maybe we want to run a function on that input, an arbitrary function on that input before we copy it to the output. Oh, 150. Well, okay, maybe we want to fill the output data structure with some value. Maybe we want to zero it out. That's a lot. That is a lot. How many of you want to write 200 functions that are just while loops? I don't. I really don't. And in fact, I could think of an arbitrary number of data structures, an arbitrary number of algorithms, and I'm sure the users of your software, of your libraries, do as well. And it turns out that if we want to cover all our bases, we have this number of functions. And they're just while loops. They're just while loops. Why are we doing this? And they're all called copy. It's stupid, right? Okay, maybe it's not stupid. I guess my slides are telling me we're missing something, so we're probably missing something. So let's back up. All of these while loops look very, very similar, right? We have some sort of schema that looks like this. We have an input sequence. We have an output sequence. As long as we have stuff to work on, input and output, then we copy them and we bump our iterators, our pointers, and we return the output. All right, so what can go in that input sequence? What things can go in that input sequence? Well, we've seen examples of a pointer to a node inside a linked list, or an iStream, or you could imagine any number of them. What about output? What could go in output? Well, very similar. We can't put an iStream in output. That doesn't really make sense. We could put an ostream in output. We could put a sync function that just takes in data and does nothing, sort of dev null function. That's kind of cool. Not very useful, but on its own, but still pretty cool. You could imagine any number of these. And I keep saying these. What should we call them? Well, we should call things that kind of look like this iterators, all right? Because we're iterating through the data structure. Now, we're going to start, slow down a little and see that iStream and OStream are not entirely iterators on their own, but we're going to get to that very, very shortly. Okay, so we take our schema, and because we have things that we're changing in the input sequence, types that we can use in the output sequence, we template on that instead of our type T. You're all familiar with something that looks like this, right? This is very similar, or this is very easy. This is very similar to things you've seen before. It's a little bit verbose, but it gets the job done. Now, we still haven't seen how to write output, or read input, increment, and increment. So let's define that. Let's define a function that just reads input. Call it source. Let's define a function that takes input and writes it, sync. You can see for a pointer that looks just like a star. For the no data structure, that looks like the caret or the arrow and then value. And incrementing the output and incrementing the input, that's also pretty similar. We can define a successor function that gives me the next iterator in this sequence. Okay, cool. This is, again, this is pretty easy. And I still haven't answered that question, why are we doing this? Like, it's a copy algorithm, it's a while loop. Now, of course, we only have to write one of these. But we haven't really seen much power here. If you were just doing this, you probably wouldn't go through all this trouble to take that one-line while loop and expand it to however many 10 lines that we have here. Now, we talked about input iterators, we talked about output iterators. We saw that they have to have sources and sinks, and they have to have successors. So we can define those for our types, and suddenly our code works, right? Nothing interesting going on here. Except I might add, or I might point out, this auto here is a new concepts light feature. So you can actually, these are templates. So when you see an auto here, it's just like a C++14 generic lambda. Replace this in your mind with template type name T, and that auto replace it with T. Nothing really strange going on here. It's just nice and compact, nice and simple to reason about, nice and simple to understand. Okay, so I kind of just threw that at you, right? And it wasn't really impressive. So I'm glad no one's left yet, because we're going to get a little bit more impressive. And we're going to see how iterators actually, what we've done here can actually be extended to an infinite, a countably infinite number of data structures. So let's get formal. Let's look at this a little bit more in depth. What do we need? We don't just need sinks and source functions and that. We have to define the semantics of them. So let's look at this again. This is our code. Okay. So to make this work, what does input iterator need to do and what does output iterator need to do? Okay, so every time we see an input iterator, every time we see an output iterator, we're doing something with it. Well, one really easy to see thing is comparing for equality. We need to be able to do that. It's really easy to define a type where you can't compare for equality. Just don't define that operator double equals, or make it private, or delete it. So we need to be able to do that. We need to be able to assign iterators, input iterators and output iterators. We, in fact, need to be able to construct input iterators and output iterators, so no private constructors. And of course, we need to be able to destruct whenever we construct. All right, but that's not it. Of course, we have something that looks like successor. And we do that on both input iterators and output iterators. So we need to be able to iterate for it to be an iterator. And of course, for input iterators, we need a source function, and output iterators, we need a sync function. Let's arrange these schematically. Let's have a nice table. And we can actually see that they kind of fall into groups. Those first four we talked about, those are easy, right? A lot of things do those. That doesn't make them iterators. So we might call these regular types, because they're regular. They do what we want. They're what we expect. Things like int follow this, things like double, things like iterators, things like stood string, things like stood vector. These are all regular types. The thing that gets interesting, though, about iterators is they have this successor function. And then, once we have iterators, we can define an input iterator and an output iterator. An input iterator is just something you can read from. And an output iterator is just something you can write to. These are all orthogonal. You can have a regular type that isn't an iterator. You can have an iterator that isn't readable. You can have a readable thing that isn't an iterator. But for our algorithm to work, we need all of these things. All right. So what this is, what we've just defined, is called a concept. And we haven't really formally defined it yet, despite the title of this section. We haven't really formally defined it. We've just said what's there and then kind of hand-waved, and then it's great, right? All right, so let's look at how we define concepts a little bit more rigorously. In concepts like TS, we have syntax that looks like this. We have a template type, T, and that's going to be what our concept is on. And we have syntax, concept, bool, and then the concept name, and then some Boolean expression. So what is this? It's something that takes in a type T and returns a true and false, or true or a false, at compile time. It's a predicate on types. So what does that give us? Okay, cool, right. Well, for something like regular, we have type traits in C++. We can use isDefaultConstructible to define what a regular type is copy constructible, is destructible. This little v at the end, if you're not familiar with it, that's a new C++ 14ism. Instead of having to reach into some template and do a : value and have really ugly syntax, we can just instead do a nice variable template like this. So don't get tripped up by this. This is just a value that says at compile time, is t destructible. Great. We've defined regular, except we haven't. Because this guy doesn't actually exist. That's unfortunate, right? Okay, so this whole concept thing is bogus, right? Because we can't even say something is equality comparable. We can't even say that two things double equal each other. We can't specify that. It's bogus, right? Well, okay, well, again, let's back up. What would we say in math? What would we say if we were describing this to someone? Well, we'd say for any x and y that we want to be a regular type, we can say x double equals y, and that can be used in Boolean context, as in that can be converted to a bool. We need to say that double equals induces an equivalence relation on T, so all that nice stuff you learned about back in your computer science classes, symmetry, reflexivity, transitivity, you need to have that. And finally, if x and y are double equal to each other, then they represent the same value. Because I could define a really nice equivalence class that always returns true. And that's a pretty bad equivalence class for equality. Because that would mean that all ints are equal, all doubles are equal, everything's equal. We're all equal. It's great. Except when we want to distinguish between values. So in concepts like, we actually have syntax to do every single thing, except some of it, that we want to do here. So that for all x, comma y in t, we write that as requires, and we introduce it with one of these variable lists here. For an x of type t and a y of type t, any arbitrary x of type t and y of type t, these things need to be true. Now, this isn't C++ syntax, so let's put it in C++ syntax. That's kind of cryptic, but what it looks like is we have x equals y, that sort of expression, and we can take it to a bool. We can implicitly convert it to a bool, which says exactly what I said in code. Now, how do we say that double equals induces an equivalence relation? That's kind of tricky, isn't it? We have to know about the values of x. We have to know about the values of y. We have to know about the source code and the way the algorithm actually works that defines equality. And that's really hard. That's undecidedly hard for a compiler to figure out. So we just kind of wallow on that and, you know. Yeah, so concepts light allows us to specify syntactic constraints. It allows us to say x double equals y, that is an expression that is allowed, and it has type that is convertible to bool. But it can't do these more semantic-y things, these things that say, well, double equals, that has meaning. Because any old double equals could be convertible to bool. We could have one that returns false. That doesn't make it an equivalence relation. All right. But what you see before you is a definition of regular type. And even without that really nice built-in is equality comparable, we have something that looks like regular type. There's a little bit more to a regular type. In fact, we would want something that says not equals as well, because what use is a type that says equals where we can't use not equals? That's not very useful. It's not a very good type either. You should feel bad if you've written one like that. So Readable is actually pretty similar as well. We have this new interesting thing here. We need a type, an associated type with our type t for it to be readable. We need to say that there is a value type. We can write value type and get a type for our t for it to be readable. Additionally, we need our source function. It needs to return something that's convertible to a constant ref to value type. So it could return it by value, it could return it by a constant ref. It's great. And it has to be O of 1. We can't be going out and doing a linear time search or a quadratic search to find the thing based on the iterator. That would just ruin our algorithms and make them much, much slower and would kind of throw this whole thing in the sink, wouldn't it? Same with writable. It's actually really similar as well. Instead of source, we have sync, and instead of a constant reference there, we have a mutable reference. It's great. Nothing really surprising going on here. New syntax, but things we've already been thinking about before. And finally, once we get to an iterator, we get a successor function, which we've seen before, and that successor returns a new I, and we have this interesting clause here. Successor may mutate other iterators. That's really scary, isn't it? That's really scary. If I call successor, I can't reason about the state of the other iterators necessarily. So, as I've defined iterator, you can only have one iterator at a time. Well, you can copy them around, the regular types. You can default construct them, you can assign them, but you can't store an iterator to a past value in the sequence and expect to get that same value out, or when you iterate it, expect to see the same things that you've seen before. Now, why is that? This is a really weird restriction and really strange. But if you think about streams, when I read something from a stream, and I read something from a stream again, and I read something from a stream again, there's no way I can get back to that first value. I have to have stored it already. I have to have done work on it. I have to have had some sort of online algorithm maybe that just pulls things off and does what it can with them instead of storing them. So there's no way to store some reference to some past thing in the stream. So if we want to make this work, where we have some sort of iStream iterator or OStream iterator that wraps up this iterator and allows us to read from something multiple times, the same thing multiple times, allows us to copy them around, default construct them, we need this restriction. There are a lot of other interesting input iterators as well. I've been talking about having a function that just spews out data. That's another example of this. We can't necessarily uncompute the data and get back to where we were before. All right, so this is a pretty interesting requirement here, and it's not one that concepts light allows us to express. We could get a little bit more fine-grained, of course. It can't just mutate any other iterator, can it? It can only potentially mutate iterators in the same sequence. Again, concepts light doesn't really allow us to say that. So we have to resort to these, we call them axioms, these comments in the concept. All right, so this is our code. Great. Let's make concepts aware. So, what is an input iterator? Well, we said an input iterator was something that was an iterator and that was readable. We said an output iterator is something that's an iterator and writable. Great. We have just made allowed the compiler to check at compile time whether things that people that instantiate our templates are instantiating them with types that will work with our algorithm. That's great. And it only took us 4 extra lines for our one-line while loop. So what's the point? All right, so we could play some tricks. We don't need iterator everywhere. I mean, I love iterators, but we don't need them everywhere. We can just say in and out because we see iterator and we see iterator for out. We can play tricks like that, but that still doesn't really solve the problem. That doesn't make it much better. Concepts Light provides a nice shorthand, though, that we can use to make this a little bit simpler and a little bit clearer and say more clearly what we mean. Really what we're trying to say is in and out are iterators. So let's say that. We replace that type name up there with the name of a concept. And replace that type name right there with the name of a concept. We still have the readable and writable and a requires clause. But this is actually very easy to read. And it's only one more line. So we're doing better. Now, these iterator concepts I defined, if we were just doing copy, again, this wouldn't be very useful, because I just write that while loop. But as we get more and more, as we see more and more algorithms, we start to see this as a pattern, that these sorts of things happen all over the place. We could have a fill algorithm that just writes the same value over and over and over again, something like memset, but type aware. And will work for streams, will work for sync functions, will work for vectors and lists and decks and any sort of data structure that you guys have in your code base. Great. We could do a fold function. A fold function in C++, we call this an accumulate in the STL, but it's something that takes a value and kind of squashes them all together, applies an operation in between them, and folds them all together into one. So this op here you might think of as something like plus, or something like times, or something maybe more interesting. I think there was a talk on accumulate today or tomorrow. You should all go to it. Accumulates are great. I'm calling them folds, but
I think it was yesterday morning.
It was yesterday morning, unfortunately. You all should have gone to it. All right. We could also have something that looks and finds the first value here in our sequence, something that's equal to this value. You know, we want to constrain this a little bit more, of course, because we're comparing value for equality or inequality here. That's fine. Let's ignore that for the moment. We would have some sort of constraint that value type of it is a regular type. Easy to do. But as we see, iterators and readables and writables, they're everywhere. And this will work with any of the data structures we talked about, any of the data structures we haven't talked about. This will work with any data structure. That's pretty cool. And of course, there are an infinite number of them. So let's see, as a story, say, I live on the East Coast. I write my cool data structure, Patrick structure. It's a really cool data structure. I think you all should use it, all right? So someone out here on the West Coast, they write their cool algorithm. That's called their cool algorithm, because they weren't as creative as me. And as long as we both provide iterators, or I provide iterators and they use iterators, someone 15 years down the line can just hook them together and they'll work. How many of you here have used some library from 15 years ago that didn't work with some other library from 15 years ago? And you've had to write a lot of code just to make them work together? I don't see any hands. That's a little bit disappointing. Yeah, okay. Some people are really unashamed of it, and some people, yeah. It's very tricky. With something like this will work with the minimum set of requirements that we need. We looked at our algorithm and said, what do we need to make this work? And we're only requiring those, instead of saying, oh, you have to derive from this class over here, and then you have to implement this virtual function, and oh, by the way, if you have some class that you want to use with it that isn't derived from it, you have to make your own derived type, and that's a little bit disappointing. We don't have to do any of that here. So we have a lot of algorithms, we have a lot of data structures, we have a lot of use of it. Still kind of while loops, but as we see, something like find first, looking in a code that says find first out of this sequence, that's a lot better than something that looks like this. So we can write this once, we can unit test it once, and we know it works everywhere, as long as they follow our concept. So that's not the end of the talk. That's probably the most important philosophical bit of the talk. But it's not the end of the talk, because we can go further. We can move forward. So consider this algorithm. It's called max element. It's a really nice algorithm. It takes a sequence and returns the maximum element. It's very aptly named.
Huh? Returns an iterator.
It does. Sorry, it returns an iterator to the maximum element. Thank you, Marshall. It returns an iterator to the maximum element. That's kind of important. So I want to step back and notice that we say it takes an iterator and a readable iterator. Is this code correct? Crickets. No one? Well, okay. Let's think about it. I'll tell you the answer, actually. It's not. This code is not correct. And I don't need to think about any specific type. I don't need to write any tests to make sure this doesn't, or to see whether this doesn't work. I can just look at it and say, this obviously doesn't work. And why does it obviously not work? Well, remember our iterator type. And remember that really scary comment that we determined that we really need, but we don't want. We really need it, but we don't want it. So so that max element is a really useful algorithm. You can't just say, well, that's an outlier, you don't need that. Iterator, we've determined, is a really useful concept. So I guess we can't use an iterator and a max element. So instead, let's define another concept. So we have something here, let's take it away. Boom. Now our code works. We didn't change anything except remove a comment, but suddenly our code works. That's a great feeling, isn't it? We call this the multipass guarantee, because what this means is I can take an iterator I, and it's a regular type, so I can copy around, I can save it on the stack, I can do whatever I want. I can increment one of them, and then when I increment the other, it hasn't been modified. So it's incrementing just as if the other iterator hadn't been incremented. We call this the multipass guarantee. Forward iterator is a little bit of a misnomer. It's really a multipass iterator. So we take and we add that one word there, and all that one word is remove a comment somewhere, and suddenly it works. That's great, isn't it? But this is actually really powerful. I say that kind of flippantly, but what we did is we looked at the code. We didn't test it, we didn't run it, we didn't compile it even. We looked at the code. We looked at the constraints that it says it needs to follow, and we determined that there was a bug. That's an incredibly powerful way of making software correct. We're not using proof techniques, we're not using automated theorem provers, we're not using compilers even. We're just looking at it and saying this can't work. So I have a proposition for you guys. Any type T that models forward iterator, that type T also models iterator. Now, if we go back to our concept for forward iterator, it doesn't say anything about that, does it? But, I mean, it's pretty obvious. A forward iterator is just an iterator that allows you to iterate through multiple times. And if we remember, iterator may mutate other iterators, but doesn't have to. It'd be a pretty weird concept that says iterator has to modify every other iterator, wouldn't it? It'd be kind of weird. Someone may find use for that, I don't know. I certainly haven't. So it's pretty easy to see that. All right. Now, actually, before I move on, forward iterators are really useful as well. What sort of models of forward iterator do we have? Well, we have things that are backed by memory that we can iterate through multiple times. We have a singly linked list, a doubly linked list. We have our pointers in an array. We have even something that's computing values on the fly, say that computes the next Fibonacci number. We could have an iterator that stores the previous two and then computes the next one when it increments. And as long as we store those previous two, we can increment it again. Fibonacci numbers are kind of cool, and they're a really CSE sort of thing to say, and sometimes you find a use for them, but use it as you will. But there are a lot of really useful concepts of forward iterator. And now that we can save them on the stack and reason about that, use equational reasoning on them, we can actually make a lot of interesting algorithms. For example, we can reverse a list. We can search for something in the list. We can do a binary search. It would be a pretty inefficient binary search because we'll have to loop through each time. That's like n squared or n log n, something like that. Algorithm, that's not a very good algorithm, but we can do it. And that's important, we can do it. So, let's back up, all right? Literally, let's back up. I talked about reverse. And with a forward iterator, you'd have to go and you'd have to go to the end and then copy them to the beginning. And then you have to go and you'd have to go to the 1 minus end and copy them to the 1 almost the beginning and so forth. And that's an n squared algorithm. But that's not what we do with something like an array, right? We wouldn't do something like that. So this reverse algorithm has a different function here. It has a predecessor. Intuitively, we know what that means. It means if I call a successor of something, the predecessor was the thing I called the successor of. And of course, we can't call predecessor on the beginning of the list, or beginning of a sequence, rather. We call this a bidirectional iterator, and it's, again, very similar to the forward iterator, except it has this predecessor function, and I cannot say that, so I'm not going to. That function there, when applied on the result of a successor, returns the same thing. We have an identity there. And that's really important, because otherwise anyone can define a predecessor function, which I said correctly this time, and it can do whatever it wants. It can just return the same iterator. That's not a predecessor. Excellent. So we write that word bidirectional there, and suddenly we're all good. And for something like a doubly linked list, we can just write that predecessor real easily. For something like a singly linked list, we can't do that. We can't write this algorithm for a singly linked list. Doesn't mean it's... yeah, right. We can't write this algorithm. We can write the function signature that does the same thing, but we can't write the actual implementation that we're using here. All right. So, bidirectional iterator. It's surprisingly not very useful. Forward iterator and random access iterator are all very, very useful. But another proposition, it's pretty obvious though. If T models bidirectional iterator, it also necessarily models forward iterator. Because all we did was add a predecessor function. So, great. But something more interesting can go on. If we have a type T that models bidirectional iterator, its dual also models bidirectional iterator. So what do I mean by that? If we're walking forward with successor and we're walking backward with predecessor, you could make a type that instead you walk backwards with successor and forwards with predecessor. Now, that's also a bidirectional iterator, and we call those reverse iterators in C++. The term dual is one that we might use in modern algebra when defining sequences and defining relations. But it's just a reverse iterator. Excellent. So this is all pretty cool, right? Iterators are pretty cool. I like iterators. Great. For a lot of you, this is probably not new. So why am I even saying it? Well, let's look at this one then. So we can define any algorithm with forward iterator. For example, that reverse, I described how you'd write a reverse sequence with a forward iterator. Now, unfortunately, something like this increment, we can do it. We can increment an iterator n number of times, but it takes O of n operations. Whereas if we were using a pointer, it would only take O of 1 operations. It's a single thing to do there. But unfortunately, we have no way of saying that, because our iterator is wrapped up in this successor function, right? And so, unfortunately, we're not making use of the full power of our pointer. So that means our binary searches are not going to be log n, and that's just not acceptable, right? This whole iterator thing would be horrible if we couldn't make a log n binary search. Similarly for a decrement, of course. So let's define something that makes use of the full power of our random access iterator. And this is a lot more stuff here and a lot more comments, and comments are great, right? So we have something where we add n to an iterator, and it takes O of 1 time, and it returns an iterator. That's the syntactic constraint. But that means something. So when we add 0 to that iterator, it returns that iterator. When we add some positive n to that iterator, it's like applying successor that number of times. And when we add some negative n to that iterator, it's like applying predecessor that number of times. Similarly, we can define subtraction, which is the opposite, and we can subtract iterators and figure out what the distance is between them. So we can do something like a binary search. My actual favorite algorithm here is an upper bound. So an upper bound takes in a sorted sequence and will return to you the first element that is greater than the thing you provided, that x right there. So it's going to say sorted sequence, and we're going to look for all the x's, and as soon as we get something that's greater than an x, we're going to return an iterator to that. So I don't want to convince you this is correct, because it's really easy to get off by 1 errors, and that's in fact why I wrote this recursively instead of iteratively, just for my own sanity. But you could easily transform this into an iterative solution that's constant stack space. But we couldn't have done this with our bidirectional or our forward iterator. This will take O of log n time, rather. So, random access iterator is pretty cool. This is something like a vector, right? We can just jump anywhere in the sequence. Or something like a counting iterator that starts at some natural number, and as you call successor, it increments it, and calls predecessor, it decrements it. We can do that in random access time. We can't do something like that for a linked list, though. So another proposition. When we have a random access iterator, it also models bidirectional iterator. Really simple to see. Right? We define successor to increment by 1. We define predecessor to decrement by 1. So what we have here is a set of syntactically unrelated concepts, but they form a sort of hierarchy, the iterator hierarchy. And this is what we've had since 1993, whenever the STL was created and then added to the standard. We've had something that looks roughly like this. This is the state of iterators for a very long time now. So you're probably all used to this, although you might not have thought about it in this sort of abstract or algebraic sort of way, but you're probably used to this. Okay, so I have about 20 minutes left, and so we're going to talk a little bit about how we can extend that. We're at the status quo right now. How can we get further? All right. So, as a pop quiz, this is our second audience interaction section, so I do want responses. Can I memmove some sequence, some random access sequence of bytes? Can I call memmove on it? I see some head shakes. No? No, we can't. So let's look at the concept. Let's make sure, right? Just to convince the rest of you who haven't shaken their heads yet. So for something to be valid, we need to look at the concept and see what the concept says is valid, because anything else is totally fine. We cannot rely on it. So our concept for random access says we can add some number to it, we can subtract some number to it, and we can find the distance between them. Also, we have a nice ordering there. It doesn't say anything about memmove, right? It doesn't say anything about pointers. It doesn't say anything about that. So the answer is no. Now, why would we want to use memmove at all, right? Memmove's this weird C function. I don't know if any of you have used it before. Because it's fast. Exactly. Memmove is optimized by your compiler vendor, for your specific architecture, in a way that our simple copy loop might not be, depending on how good our optimizer is. Our memmove is probably much faster. So the answer is no, but we want it to be. Okay, so actually let me present a counterexample. So if that did convince you, that sort of reasoning, because maybe something more subtle is going on there, that there is some sort of way we can use memmove. Let's throw an example of a segmented array, an array that is a vector of vectors, and show that we actually can't call memmove on this. So I'm going to have a vector of vectors, and I'm going to add this invariant that each inner vector, except the last, has to be the same size. So it's like we're taking a sequence, a vector, and we're splitting it up into constant sized chunks and just putting them off on the heap. So we can define an iterator for that. We can even make it random access. I'm only showing you the plus here, but the minus is similar, and the subtraction between two iterators is also pretty easy. Convince yourself that this is O of 1 time, like we need for a random access iterator. There's an ugly integer divide here, and potentially on some architectures, maybe another ugly integer divide, but it's still fine. It still will work. And it's still O of 1 time, so we're still satisfying our constraints, even if this is a kind of suboptimal implementation. Okay, so that's what our segmented iterator has. But what does memmove need to work? Well, we need trivially copyable data. We had that with our bytes, so that's fine, right? We couldn't do this on something like a standard string, because standard strings are not trivially copyable. And we need those things to be contiguous in memory. Now, what does that mean? We have a way of describing memory now. We have iterators. We have a way that describes any sort of memory you can imagine. So we can describe this in terms of iterators. All right, so if I have an iterator I and I have an iterator j, what I want is some function pointer from, say. that when I do something on the iterator, it's as if, and convert it to a pointer, it will be the same thing as converting it to a pointer and doing that operation. Similarly for minus and distance computation. So, in other words, we want pointer from to be an isomorphism that preserves the algebraic structure of our memory. And we want that to be an isomorphism from our iterator to pointers and back again. So, pointer from for pointers is pretty easy, right? That's a pretty easy function to write. I'm dead confident that I got it right. A slightly less easy one to see is maybe for some reason you have a iterator that is a pointer and an offset. Maybe you were like me and you were experimenting and seeing if that helped alias analysis in your compiler and you find out it doesn't. But then we have our pointer that's first and our pointer that's a second. We add them together. It's still not a hard isomorphism, but it's still an isomorphism. And you can look at that and see, yeah, there's a one-to-one correspondence between pointers and iterators. And that if we do some addition in our iterator space and we convert it to a pointer, it's as if we did we converted it to a pointer first and then did the operation. Okay, that's great. So actually, before I move on, what we've just seen here, shows that segmented array cannot have such an isomorphism because we have arrays living off all the way in the heap, all here and there, and we can't bridge over those gaps using pointers. Because if we increment our pointer and we're at the end of a segment, then we might be running off into memory doing whatever we're going to do in an undefined behavior lane. It's just not good. So we have a different set of constraints now. We need this pointer from function. And that's something that returns a pointer. And that pointer has to be an isomorphism, as we've discussed. So we have a nice comment there that says that. We trust that people are going to do that. All right. So we write our contiguous iterator. We have to make sure that they're trivially copyable and they have the same type so we don't have weird slicing problems. And we can use our memmove, and it's going to be fast. This is going to be fast for things that it can be fast for. For things it can't be fast for, it's not going to be fast. But it will work because we're overloading our copy and we're specializing our template. Excellent. So this is actually in C++17. Not as I've described it here with this pointer isomorphism, but something that does the same thing, contiguous iterator. And you can use this today. You can write your trivially copyable algorithms and do all this wonderful fast bit splitting on any data structure, as long as it says it's contiguous. So as long as there exists that isomorphism, you can do that. It's coming in C++17. So I really like that segmented data structure. I think it's just really nifty. We have one of those in the standard, actually, but it goes by an unassuming name called unordered map, unordered set, names like that. Those are actually just arrays of arrays. They don't have that additional restriction where we say they have to be the same size, but this actually comes up quite a lot. A deck, too, yeah. That's a great way to implement a deck. It's not a great way, but it's a fun way to implement a deck, where you have an array of arrays. You could do it with a ring buffer or something like that, but it's a great way to implement a deck. So, our segmented array again, simple, nothing weird going on here. But if I were to write, or use just the iterator we provided before, I'm not going to be able to take advantage of that contiguous iterator optimization that we just did. I mean, we spent a whole 5 minutes showing that we couldn't take advantage of that. But I want to, because I know those inner arrays are contiguous, because they're vectors. So really, if I were writing this by hand, I'd say something like, okay, so if we're in one of these inner arrays, let's call it a segment, say, if we're in the same one, then just copy it. We don't have to worry about segmentation at all. If we're traveling across segments, first we get out of the partial segment that we're in, we do a really fast loop across all the inner segments, and then we clean up at the end that maybe partial segment that we have at the end. That's what this function here is doing. And this is how you'd write something like this. And this is a really common pattern when you're dealing with segments of any sort. So this is how I want to write this. But unfortunately, that segment function there, that local function there, that begin and that end there, that's not something that we have in random access iterator. That's something we're exposing. Our iterators are just saying, we have a flat sequence and I don't know anything about the structure inside of it. Except maybe for contiguous, we know that it's laid out in memory in a certain way. So we can define a segmented iterator concept. And this segmented iterator concept allows us to write that code we just saw. So, okay, what do we have? Let's back up, right? We need a segment iterator, and that's going to be the iterator on our outer type. We need a local iterator, and that's going to be the iterator on our inner type. Those both need to be iterators. They can be stronger, they could be contiguous, they could be random access, they could be forward, but they at least need to be iterators. And I'm kind of eliding this, but we need segment iterator to provide a begin function that returns an iterator and an end function that returns an iterator. We call such a thing a range. You might have heard about them. They're kind of popular nowadays. We also need these functions local that will take a segmented iterator and return what it's currently pointing to in the inner array, and a segment that gets out of that segmented iterator the pointer to the segment. So actually, let's look at that. That might be a little confusing. So if you remember, our segmented iterator was a struct of an outer array, which we said was a pointer to vector of t, an inner iterator, which I just defined as a size t, an offset from base. So let's do something here. Size t isn't a readable iterator. It's an iterator because we can define a successor function on it, but we want it to be a readable and writable iterator. So let's take it and convert it to a type t star. And so where we do that is down here in this access function. You write this gnarly thing once, and we can get the local iterator out of that pair of segment and local iterator. We can write a segment iterator, which is even simpler. It just returns the segment iterator, which we've called spine iterator. And we have this thing here where I'm defining a begin function and a pointer to a vector of t. That's kind of ugly, but anything else wouldn't fit on slides, so you're going to have to live with it. Don't write this in your production code, please. Please. So this type, now our segmented iterator, works. And we can write that function we saw before on segmented iterator, and we can take advantage of that optimization, that memmove that we saw before, because we're just delegating to an inner copy function that can figure out what the iterator category is based on the concept that the iterator satisfies, and just do the right thing. So if, in our case, our inner iterator is contiguous, so excellent, we get that bit splitting stuff. If it were not, maybe we have a doubly linked list inside, something like a hash table might do that. Then this will still work, and it will still do the right thing. It won't take advantage of the optimization that it can't take advantage of. It will still be correct. But back up, segmented iterators are exactly how we'd want to parallelize operations on this data structure. We would want to take one of these segments and feed it off to some thread, and take another segment and feed it off to some other thread, and take another segment and feed it off to some other thread, and wait until they all do all their work and converge back together. That's exactly how we want to parallelize this. In fact, we can almost write that in C++14. Now, we don't have a task pool implementation, and our futures are not good enough to really do this well. But if we're using something like TBB, Intel TBB, we can write something like this. If we're using a less impoverished futures library, we can do something like this. So I'm going to write this in the abstract. Let's get a bunch of threads that we can use. Let's do our normal segmented stuff. It wouldn't fit on one side, so we have two branches of our if. In the first branch, if we're in the same segment, why spawn it out to different threads? Just do it. Do it in place on this thread. Or if we have a segmented iterator inside a segmented iterator, well, maybe you can do that. That would be pretty cool. You can have that arbitrary number of times and really confuse your friends. You can, so if we're not in the same segment, we have to do something a little bit more interesting. But again, it follows the same structure that we saw before. Instead of calling copy, we farm him out on a task pool for a thread to pick up. And for each of those three different segment iterators we talked about before. So when we're done with this, this is asynchronous. We could add maybe a task4.go or something like that. Maybe these are blocking, however your library works. But this will write to out the value that we want, and we'll parallelize it in exactly the way we want. Fortunately, as an author of this algorithm, I didn't need to know anything about that. I just needed to know I can break it up into different segments. And I'm just going to trust that the author of the data structure knows how to break it up into different segments. So I don't know how many of you use segmented arrays very often. They're unfortunately not that common. When we're doing parallelized algorithms, often we use vector. Why do we use vector? Because it's all contiguous in memory, and we can reason about the cache behavior that we have. Fortunately, actually, wait. Segmented iterator is great for parallelization. We wrote that algorithm, and it's suddenly parallel. And it's parallel, and it's correct, and it will work for any segmented data structure. Contiguous iterator is great for just blasting out bits, copying them. If we know they're contiguous, we can do some really nice optimizations on them. Okay, no las dos. Why not both? So we call this a cache-aware iterator. And it's an iterator that is both segmented and contiguous. Because it's segmented, those segments could be cache lines, or we really want multiples of cache lines because our type T may not fit nicely in a cache line, and we still want correct behavior. But if it does, then those segments could be cache lines, great. And it's contiguous, so we can, we know that it's all in memory, so we can say any pointer, any vector, is really a segmented iterator. So if we write our algorithm as we did before, each thread is fed its own set of cache lines. By the way, we split them up. And we know that no two threads then will be writing to the same cache lines. So if we do this, and if our segmented iterator is correct, then we have absolutely no false sharing. Now, I didn't write my algorithm to do that. It just happened. That's really nice. This just happened. And as someone who is not a guru in parallel algorithms, I can still implement this and have implemented this and seen performance benefits. Now, it's nowhere near something that you might do in high-performance computing, but if you're just writing a desktop application or some small application, you want your library to do this for you and just spawn them out to different threads. You know, you could have a more articulated library that allows you to control that a little bit more, but we have this nice benefit of no false sharing. And false sharing is one of the really, really problematic ways that we have with performance. So that is how we can extend that. And unfortunately, to actually make that work requires a lot of code, and it requires another 30 minutes. And I don't have another 30 minutes. So instead, what I'm going to say is I've started to write these up in a series of articles, going from 0 and saying everything you could possibly want to know about iterators, something I can't fit in this 1-hour talk, and culminating in this cache-aware iterator and what performance benefits we can gain and real actual numbers. So if you're interested in that, at the end I'm going to have my webpage up. The introduction to that should be going up tomorrow, assuming conference doesn't get in the way. It's all written. I just need to become a web programmer. But of course, no good work happens in a vacuum. And there are tons and tons of resources on this. But these are 3 things that you might find really useful. So if you're interested in that, Google them, Accept Elements of Programming. That's a book, buy it. The iterators I presented here are based on, but a little bit different than the iterators and Elements of Programming. I think Nevin Lieber is here, so
Sadly, Nevin is not.
Oh, okay. So he's not here, but email him and thank him for contiguous iterators, because they're great. They're really wonderful. And they're in C++ 17. I guess that's my cue to leave. So we are exactly an hour in. You probably want to get to the plenary session. So if you have questions, I'm going to ask you to come up and ask them to me now so we can get everyone else leaving if they want. All right, thank you very much.